Okay, so we have spatial operations, which are the basic components of spatial analysis. In any given spatial analysis, performing a series of individual steps, including clipping your data, intersecting your data, and querying your data. Spatial operations can have the following three scopes: local, focal, and global. Local analysis operations use data at only one input locations to calculate the value of the output at the same position. Local analysis operations do not use any values or attributes of adjacent areas. For example, calculating the population density within the state of California is a local analysis operation. It does not include other states around California in that calculation. Focal analysis operations, sometimes called neighborhood operations, use the value of the input location as well as values from areas that surround the input location. For example, in calculating the total number of bordering states in a US map layer, the output value for any particular state depends on its neighbors. Finally, we have global analysis operations, which use all data values from all participating map layers to calculate the value of the output. For example, suppose one wants to rank each state in the US based on population density. A global analysis operation uses values from all states in the map layer in the calculation to evaluate the rank of any particular state. Spatial operations tend to fall into two primary categories: proximity and overlay. Proximity operations for spatial analysis share similar characteristics as they do for spatial queries in that they evaluate distances from features. An overlay operation is a spatial operation in which two or more data sets are superimposed on one another to assess the relationship between features that occupy the same geographic space. Overlay operations also share common elements with other spatial query operations. The primary difference is that overlay operations use a spatial query to create new data sets. So highlighted in blue will be what we are covering this week. First off, we already covered the selection functions in the last section. So, selection, we're identifying a subset of features, so that would be select by attribute or by location. And then we'll be going over buffering, which is a proximity tool, but is also an overlay operation. And then we'll be going over dissolving, which is a generalization tool. And then next week we'll go over the rest of these. And again, many operations incorporate both the attribute and coordinate data. Attribute data are part of the definition of spatial objects according to Bolstad. As I mentioned earlier, proximity operations have to do with determining the distance between features. So in some instances, we can use select by location, though there are situations in which the select by location tool won't work, such as which sections of trails are within a distance of 50 yards of endangered salamander habitat. In this case, it would be necessary to use the buffer spatial operation. Buffering is an operation that creates a buffer zone and is useful for proximity analysis. A buffer is a zone around a map feature with an area calculated using distance or time. Buffering may be applied to point features, line features, or polygon layers. However, the output of a buffer operation will always be a polygon layer. So again, the buffer spatial operation, though it is an overlay operation, it's also a proximity operation, and it has to do with the determining distance between features. We can identify features in one layer that are within a specified distance of features in another layer. We can also identify areas that are within some threshold distance from the features in 2 or more layers. There are a few different types of buffers, and so I'll go over a couple of them, and then in the Bolstad text, they include a few more that you can review when you do your reading. Here we have a fixed distance buffer. Every feature that you are buffering gets buffered by the same distance. If this is a streams layer, it doesn't care what type of stream it is, or the size, etc. Every feature gets buffered by that same distance. So whether we're using points, lines, or polygons, you're going to apply, let's say, a 20-meter buffer around each point, or a 20-meter buffer around each line, or a 20-meter buffer around each polygon. And again, those output buffer features are always going to be polygons. A location is either within a distance away from one feature or it isn't. So here we have a multi-ring or a nested buffer. So this buffers at multiple distances. Let's say it'll buffer at 1 mile or 2 miles. We would use this in the case where different actions are required at different distances. Bolstad explains that we commonly see this type of buffering in hazard waste sites. We can suppose threshold levels have been established with various actions required for each threshold. Areas very close to hazardous waste sites require evacuation, intermediate distance require remediation, and areas further away require monitoring. And so we could see here, we have that first buffer zone, the second, third, and fourth, and then further down along the line, once you've created those layers, you could then classify them and have them represented by different colors, which then you would insert a legend to explain each of those threshold zones. Here we have an example of variable distance buffers. As indicated in the name, the buffer distance is variable and may change among features. The buffer distance may increase in steps. For example, we may have one buffer distance for a given set of features and a different buffer distance for the remaining features. This image illustrates the creation of buffers around the Mississippi River Basin. These buffers may be used to analyze or restrict land use near rivers. We may wish to increase the buffer distance for larger rivers. The increase in distance may be motivated by an increased likelihood of flooding downstream, or an increased sensitivity to pollution, or a higher chance of bank erosion as river size increases. As we can see here in this table, we have a larger buffer for the largest river in this basin, which is the Mississippi, of 100 kilometers. We have a buffer distance of 75 kilometers for the medium-sized rivers of Ohio, Tennessee, St. Croix, Illinois, and Wisconsin. And then we have that 50-kilometer buffer distance for our smaller rivers of Missouri and Arkansas. And then as we can see in the image here, we have that 100-kilometer buffer zone. We have the 75-kilometer buffer zone, and then we have the 50-kilometer buffer zone. We can also apply buffers to raster data sets. This entails calculating the distance from each source cell center to all other cell centers. Output cell centers are assigned an in value wherever the cell-to-cell distance is less than the specified buffer distance. Those cells that are further than the buffer distance are assigned an out value. Bolstad explains that raster buffers combine a minimum distance function and a binary classification function. A minimum distance function calculates the shortest distance from a set of target features and stores this distance in the raster data layer. The binary classification function splits the raster cells into two classes. those with the distance greater than the threshold value, and those with the distance less than the threshold value. So if we're looking at this image here, we can see that we have that center cell, and then we have our output cell size of 5 and our maximum distance of 100, and then these buffer zones have then been classified by color, and so we could see 0 to 5 has this orange color, all the way to 96 to 100, which has that blue color there.